Good morning, everyone. Welcome back. I hope you had a great weekend and we're ready to get started on today's fun session. We're going to talk a lot about quantum chemistry today, and it is a great chance for you to ask all your questions that you might have on this very exciting topic. I would love to welcome Dr. Robert Ledoux, who is the former program director at ARPA-E, which is the Advanced Research Projects Agency for Energy. And he has had a diverse interest from nuclear fission to fusion power, transportation modeling, sensor development, and very recently quantum computing and quantum chemistry. And he has most graciously agreed to moderate this panel. And I'm going to let him introduce himself more and to introduce the rest of the speakers. Over to you, Bob. Welcome.
Well, thank you so much for the introduction. That was lovely. I'll only add that I'm looking forward to being the incoming director of Quantum New Mexico Institute, which is a collaborative effort between the University of New Mexico, Sandia, and Los Alamos National Labs and industry to really try to drive innovations in quantum science and technology. And just to leverage your points, your initial points somewhat, I would say that this section explores probably one of the most promising and almost one of the most technically demanding applications of quantum computing and computational chemistry. And as many of you know, one of the founding motivations of quantum computing was, as Richard Feynman says, let's use a quantum computer to simulate a quantum system. So that is the big, bold vision that we want to look at today. Now, our goal today is to cover, I hope, what is actually working? Are we on track? What's missing? How might we realize this long-term promise of quantum chemistry, which includes everything from catalysis, materials, energy, medicine, etc. So let me introduce now our distinguished panelists, and I feel so fortunate to be part of this panel. So first, let me introduce Dr. Mario Szegedy from Rutgers University. Mario is a distinguished professor in the Department of Computer Science at Rutgers University in New Brunswick, New Jersey. His research primarily focuses on quantum computing, computational complexity theory, and recently on AI. His prizes include the Gödel Prize, the Paris Kanellakis Theory and Practice Award, and the Test of Time Award at the 2021 IEEE Foundations of Computer Science Conference. I'm sure he's going to have a lot to say about quantum computing here. And next, I'd like to introduce Dr. Kirstin Doney from Lockheed Martin. With a bachelor's in chemistry and astronomy from the University of Texas at Austin and a PhD in astronomy from the University of Leiden, Dr. Doney's research has focused on molecular spectroscopy and astrochemistry. Quantum chemical calculations have been an integral part of her research to identify and understand molecular energy levels and structure. So fantastic applications of quantum chemistry. Next, we have Dr. Kubra Aydeniz from MITRE Corporation. Kubra is the principal quantum algorithm specialist at MITRE Corporation. She conducts research on quantum algorithm development for various quantum hardware architectures, benchmarking them on current quantum hardware. Some real practical knowledge there. She received her PhD on theoretical high-energy physics from the University of Tennessee, Knoxville. And before joining MITRE, she was a postdoctoral research associate at Oak Ridge National Laboratory. Great. And I would say, Kubra, I'm a nuclear physicist, but not a theorist. So good to have some high energy physics in there. Okay. Now let's begin the fireside chat. Let's begin on an aspirational note before we get into the weeds. So I'm going to ask each panelist sharing one compelling example that illustrates the promise of quantum chemistry on a quantum computer. And in particular, imagine we have right now a utility scale quantum computer. What does success look like at this point? And what is one problem that would truly be transformative if quantum computers could solve it accurately and completely? So Kubra, would you do us the honor of starting off?
All right, my pleasure. Hello, everyone. Thank you for joining this session. So when we think about the quantum utility, I think we want to see some real world examples that we can experience as an everyday user for anything that we are interested in. And when the scientific community starts utilizing quantum tools in their toolbox when they are trying to understand the molecular structures or conducting their experiments or creating new materials. So I think that's where the success comes into play. We want something that is going to improve upon the currently available amazing classical tools and that the scientific community has already been using and have experience with, but they want something that's more advantageous compared to what they have been using. This, in terms of chemistry, this will be advantages or improvements in terms of accuracy or in terms of energy efficiency or computational efficiency and so on. So all of these criteria are important, but I think the success is going to look like when we are seeing an example that we can leverage as a standard person, not a scientist or someone who is already dealing with all these kind of stuff. So one example, I know it's a cliche for everyone, but one example that I have been very interested in, and I think it has some everyday impact in our lives, is that the nitrogen gas turning into ammonia by bacteria. And this process is not well understood, so we cannot repeat this process without utilizing an intensive amount of energy. So this example is, I think, would impact a farmer, for example, because it's going to impact the fertilizer production and it's going to impact energy usage. And so for a standard person, it's going to be impacted as well. So I think this is an important example, and you can, of course, find other cool examples, and finding this killer application itself is a challenging problem, because it's a $1 million question everyone is trying to solve. So I think this is a good start for us. And
Great.
I think that's how the success is going to look like. Can an everyday person experience that advantage?
Wonderful. Thank you, Kubra. Mario, your thoughts? Mario, you're muted.
Yeah, I am muted. No, I am not. Yeah, thank you very much. So I am not a chemist, but actually I hear that even we don't understand the water. I mean, how, so actually just understanding water would be already a achievement. But anything which would show quantum supremacy to classical methods, like classical algorithms run for an hour for a week and quantum algorithm runs in 7 milliseconds, that's already quantum supremacy. So, and yeah, so even the nitrogen bond or any of those, yeah, so could be.
Great. Thank you, Mario. Kirstin?
So I am a chemist, so I do get to kind of go along with the water, particularly for we have really good methods in quantum chemistry in classical, but we usually have to make that trade-off between something that's going to be really efficient and really accurate versus something that's going to be computationally expensive. And so we're really good with small molecules, but small molecules aren't going to be everywhere. Astronomy was really good because it really is small molecules, but we're starting to find bigger ones. And if we really want to understand them, particularly molecules that we can't really create in the lab, that are big and radical, we're going to need that accuracy, but something that's not going to take a year to calculate. And I think quantum computing is going to get us that advantage. We're maybe not there yet, but we're on the steps there. We've seen some papers out of IBM where they're starting to get bigger molecules or heavier atoms. And so I think that's kind of where we're going. And I think there's going to be an advantage there.
Great. Thanks, Chris. Well, I'm going to throw my hat in the ring here, and then I'm going to have a follow-up question, Kirstin. So I didn't hear anybody, but I would have thrown in time evolution, like a true fundamental model, not just of energy surfaces, but of actually reaction kinetics. So I'll ask each of you. I'll start with you, Kirstin. Okay. So besides molecular energies, and so on, what would be something completely new, maybe, in chemistry that would really, really get you excited. Not that that
So I
isn't
think
exciting, but
that
yeah.
is very exciting. But I'm with you on that, the time evolution. So like a TD-DFT kind of experiment where you can see the reaction mechanism. You can go between a ground state and an excited state. A lot of times they're going to struggle with that because it's a really big Hamiltonian. And I think, having a quantum computer, which is, a quantum system solving a quantum problem, you lose some of that difficulty that classical is going to see.
Kubra, Mario, would you like to add anything to that?
I just wanted to say, like, one of the examples is like the drug discovery or any material discovery. So the amount of time that is being spent on those kind of discoveries is exhausting, because the way it works right now is someone tests a design in the lab because they are larger sizes that classical tools cannot efficiently be utilized. And so we have to test something, and then if it doesn't work, we have to come up with new designs and so on. So I think material discovery in that sense would be, again, crucial, and it would save a lot of time. I know that AI is actually currently being utilized for this, for speeding up these processes and making it more efficient. But I think quantum computing also would play a significant role in those type of efficiency.
Great, thank you. Okay, so now we're aspirational. Now we know what we want. Okay, so now I'm getting a little deeper into the weeds here. So what are the biggest challenges today in using quantum computers for chemistry? So for example, is it limited by the number of qubits, the state of the art and error mitigation, the algorithms themselves, all of the above, something else? So if you had to really drill down today, what's the biggest challenge? So I'll start off with Mario. What do you think is the biggest challenge for us getting there?
Well, so I have no doubts that the limited number of error-free qubits is the biggest obstacle when we want to scale up our efforts to industrial levels. Perhaps the good news is that the devices on all platforms are developing. Cold atoms are promising, in my opinion, and building quantum channels between separate devices as connecting devices could be also a big thing.
Yeah.
But patience is necessary because probably there are still like significant inventions are on the way to get clean qubits. And by the way, it's not only that the qubits should be clean, but also they shouldn't decay quickly, because we need to run deep circuits. Now, error mitigation, which is not to be confused with error correction, because error mitigation does not prevent the decay of the device's state, is unfortunately only a bridge solution for the next few years. Like it scales very poorly with the circuit size and depths, especially with the depths, and and has a few other problems. For instance, it cannot handle every type of error. So this is an inherent limitation. I mean, mitigation helps us to push the number of the number of qubits or any numbers a little higher, and it has a place, but in my opinion, it should take a second seat, and it will never be a primary player. This is just my humble opinion, since the basic rule in science is that you never say never, and there is symmetry verification and other techniques that might tell a different mitigation story, but that's my side of mitigation story. Now, I would like to expand, however, on the very interesting case of development of quantum algorithms. The quantum chemistry problems are not one kind. So it would be a mistake to confuse problems of tracking the evolution of a quantum system, which is called the Hamiltonian simulation problem, with finding the ground energy or ground state of a quantum or a classical system. So this is called the minimum energy problem. And so this later problem is a minimization problem. And so I'm a complexity theorist. So complexity theoretically, it belongs to a very different class of problems than the Hamiltonian simulation problem. But the huge difference is that the Hamiltonian simulation, there are polynomial time quantum solutions, which are constantly being improved by Andrew Childs and others, like several researchers. And just as we speak, there is a nice result published in Nature about Lindbladians. But so algorithmically, we are doing super well with Hamiltonian simulation, although, of course, there is a lot more to be done in special cases. But on the other hand, the ground energy problem splits physicists and computer scientists big time, because physicists say that nature is able to solve it. Many systems settle at their ground state, so we should be also able to solve it with a quantum device that simulates nature. On the other hand, computer scientists argue that this particular minimization problem, at least as it is stated precisely, belongs to the wrong complexity class, because it's not tractable even by quantum computers, this QMA. So in particular, we think that no wonder that we see barren plateaus and other issues when we run proposed solutions, such as variational eigensolvers divided by quantum chemists. So my take on this contradiction is that both sides are partially right. Nature finds ground states efficiently for specific systems, those with large spectral gaps or small degrees of freedom, but not for arbitrary Hamiltonians. And so chemically relevant systems are not worst case instances that we complexity theorists like to think about. And we should understand much better how we can exploit these structures. And this is future work, and I would like to leave the solution of this fantastic puzzle to this incredibly talented audience.
I hope everybody's listening out there. That was a great overview. So, Kubra or Kirstin, would you like to add anything to that discussion?
I think
No.
you summed that up
Yeah,
really
Mario
well.
summarized.
But I will ask Mario a question on that one, if you don't mind me just quickly following up. So where in this spectrum does something like QPE lie? Because QPE, I would have thought quantum phase estimation, I would have thought as a solution to the ground state was on better polynomial grounds. Correct me, what am I misunderstanding there?
So you are saying that with quantum phase estimation, we can solve ground state problems? Well, I just don't know about this, that we can solve that.
Yeah. Well,
Maybe we can, but I don't know about that.
Yeah.
I mean, there are these, we can take it offline. But
yeah, that'd be great. Okay, I'd love to hear that formal mathematical take on it. That's wonderful. Okay, so I'm going to jump off to a different topic now, related, but it's one that I feel very strongly. I'm having stood up a program at ARPA-E and still working on it, and that is really what's the community? So chemists and quantum algorithm developers truly communicating today? And if yes, how do we make it better? If not, what the heck do we do? So, Kirstin, do you have any feelings about what's your thoughts on that?
I think, at least my experience so far, is the community is mainly more hardware driven. So it's still mainly like quantum computer experts and software experts doing chemistry, but you're starting to see more chemists being pulled in and kind of, I don't want to say converting them to the dark side away from their day jobs, but they're starting to get more influence, and they're starting to help gauge and craft those algorithms, which I think is really what the community needs, because you want to kind of get that influence from the people who are going to use it and who kind of knowing how those chemical bonds are going to have shape, so that when they build the algorithms, they're really gearing them towards the chemistry that's going to be taking place, because it's a slightly different problem than if you're just doing a normal quantum calculation or a normal on a quantum computer, right?
Yeah, so great. So, I mean, just may I ask you, so do you think we need more chemists directly working with quantum computer scientists, whether algorithmically and hardware? Do you think it more is necessary, or do you think we're on a good path?
I think 4 would be nice, particularly if you're starting to pull some of the ones from the classical quantum chemistry community.
Right.
Which I think a lot of them are starting to kind of move over as hardware becomes more and more available to the public.
Kubra, what do you think?
So I think, of course, more is always good, because we want users for these quantum computers, right? And quantum chemists are #1 candidate for that. And so, but I feel like when you look at the literature, most of the first benchmarks of quantum computers have been on quantum chemistry use cases, molecular simulations, and so on. And if you look at the quantum software developed so far, almost most of their first examples are from chemistry, and they develop all these packages and tools for chemistry specific problems. And I think it's super valuable, of course, because they can be tailored to other problems like physics, like high energy physics. And so it's a good start. I don't blame them, but I think they have been part of this process from the very beginning, the chemists. But now I think we need more people on the material side, for example, because the problems are getting more complicated. We are not just we don't want to just simulate simple smaller molecules, but we want to go to the material or drug size problems right now. So I think those kind of people need to be more involved in the process so that we can even advance the existing quantum tools.
Now, Kubra, can I ask you to clarify that? Are you saying it's not just, again, solving for the ground state of a particular molecule, but are you hinting more we need to understand synthesis more, or, you know,
Yeah.
or materials that don't live on one scale? Like what's the, I mean, once you have the Hamiltonian, electronic Hamiltonian, I mean, in principle, it's all there, right? But of course, what you're solving for is different. So can you clarify a little your thoughts on like what's the part that's missing that would get you to materials versus, I think, maybe kind of just solving for ground state of molecular energies? Or correct me if I'm totally wrong.
So I think one of the challenges when we want to embed a problem on a quantum computer is mapping the problem onto a quantum computer. And when you are studying a bigger problem, for example, a material, and then you have to do some sort of approximations to fit it into a quantum computer. And I think that kind of experience is missing at this point, because current devices can only study one size of problem, but you have to reduce that problem into that size. So I think we need experience in that perspective, and it's very valuable because we have to. So the current approach to these kind of problems is to divide them into smaller fragments and do some approximations. And so if you are not experienced with that part, then it will be challenging for you.
So this raises, there's a lot of young people online. This raises a great question of what you work on. So now that we have Mario, a theorist here too. So my question on that is, does that need more physical insight? Once people get used to writing algorithms on a quantum computer, their insight will allow, even on a quantum computer, better approximations, or, which is my next question, which I'll give to Mario, or is it really a mathematical problem in which we take the best from the classical computational world, AI, and then uniquely suit it for quantum computers? So I'll give it to Mario. Like, what's the interplay to making those quantum algorithms better? You know, physical insight versus mathematical prowess, you know, et cetera. Where do you think that next leap will be? Or maybe it's just borrowing classical techniques. I mean, do you have a feeling for where you would go on this? I'll ask each of you that. Where would you go to push on that envelope?
Well, well, it's hard to answer. I mean, we need, you mean for practical problems?
Yeah, to make them practical, given the near to midterm state of quantum computers, where do we push to get them onto a quantum computer more efficiently? Anybody?
There is, because we started from the communication side. So I am now working with a doctor on an AI project, and what I see is that everything is communication. Like there is a huge possibility of miscommunicating, or so first the problem needs to be very very well discussed with the experts. So we theoreticians we cannot invent any, and so we have to understand what the problem is to make sure that we are not solving some too general problems, problem. And actually, like our quest, like as a quantum algorithm designers, are usually to invent new general algorithms. So these are not general algorithms that usually the experts need. And in particular, like in chemistry, it seems like that there is and maybe we get to that there is like a lot of classical information that can be processed classically, like protein folding. You don't need quantum computers. So we have to find the quantum core of these problems. And so that's also, so I don't know what happens when like we really like peeled off like all the non-quantum and all the everything, and then like there is a very specific problem at hand, and then what I would do, I guess I would just start to think, quite frankly, and just try to apply, I don't know, like just my general intuition about quantum algorithm design.
Yeah, thank you. Kirstin, Kubra, any further thoughts on that?
I think the question you asked is something we are all trying to figure out these
Yeah.
days. And
Yeah.
so address these type of questions. So every time I see someone different than in my field, even if they're my friends, I bug them all the time. Okay, what are the challenges in your area? So
Yeah.
I'm trying to understand how can quantum computing improve their problems so that they can all utilize those type of tools. Because I'm not an expert in every area, you know, so it's always mind-blowing to see what they are actually experiencing in their work that you never think of. So it's always good to communicate, as Mario mentioned, and always collaborate with people from different fields. And I think that's what the field is evolving to. The quantum hardware companies, software companies are trying to make the quantum computers as user-friendly as possible, so everyone in various fields can utilize those tools.
Yeah. Well, I'm gonna launch off from that, from my outreach of a giant tension I feel, and that is between the generalization, which you were just alluding to, Kubra, like making standard tools, you know, standard compilers, versus, given the state of hardware, maybe you should specialize your solutions to what's going to be the hardware in the near to short term. So, for example, the breadth of the quantum circuit versus its depth. So this question is, my next question is it important at this point for the next, let's say 5 to 10 years, to co-design quantum algorithms alongside the hardware to most efficiently use them? Or is a better take, the hardware will get there, let's just generalize as much as we can? I have strong feelings on this, which I won't state, but I would love to know your opinion. So I'll start with Kirstin on that one. Kirstin, what do you think? So we optimize things for what we got in the short term, midterm, or look towards the future, you know, getting the Python compiler, well, interpreter of the future. Do you have any thoughts on that?
As a user, primarily in my day job, I'm going to go with, I would like us to optimize what we have so that we can use it while we have it, and hope that there's someone in the background that's actually trying to like improve the hardware alongside that for where the needs are not being met. But yeah, I'm gonna go with optimize with the current.
Yeah, I vote for that one too. But let's see what Mario has to say on that. Mario, should we be optimizing things for what we have, or should we just try to go for a more general solution?
Well,
if it exists.
Yes, I have a different. So I think the first priority remains to find efficient algorithms at all for all sorts of problems. And so that said, of course, there is this intermediate era where we should throw everything we can at it, like co-design, mitigation, whatever works. But in particular, when possible and practical, of course, we algorithm designers should pay attention to the hardware details, but only then. But I want to mention that actually down the food chain, there is a whole growing community that takes known algorithms and tries to optimize them for given hardware. So sometimes it is possible just simply to delegate these tasks. And an ideal situation would be if automated compilers would optimize our algorithms for the given software.
Yeah, yeah, that's great. Kubra, what do you think?
I think, yeah, co-design is significantly important because it can even help the algorithm people. Because, for example, if you have mid-circuit measurement capabilities on your device, that is that can change the way you design your algorithm. Or, for example, if you are studying a problem that is designed with continuous variable data, and if you are using continuous variable quantum computing, so if you have a hardware that is tailored for this, that's perfect. So you don't have to discretize your problem and lose all the advantages. So I think co-design is very important in all of these aspects. And of course, when optimized, that's also even better.
Yeah. Okay, so I guess we all came down on the side of co-design at the moment is a good thing. Well, that's great. Okay, so following on that, if you could pick one major breakthrough, so you're going to have to make a choice in algorithms, noise reduction, hardware architecture, anything, community, greater discussion, what one would you choose that would have the biggest impact? So right now, if you were in control, and you had to pick one thing to throw the community's effort into, what would it be? Who would like to go first on that one? Kirstin, you're shaking your head. How about you?
I think I'm gonna go with hardware architecture, just because I think one of the things is like the size of molecules that we can go after now is pretty hardware constrained. So if we can get a different architecture, we might be able to get to bigger or heavier molecules.
So when you go to different architecture, you mean more like logical qubits, or are you talking about maybe the interconnectivity, the topology is different so that you can do a more efficient calculation, or all of the above?
All the above.
Yeah.
Yeah.
Okay.
Because
Yeah.
I think at least they tend to go hand in hand for a lot of those algorithms that are currently out there.
Yeah. Okay. Agreed. Mario, your thoughts on that
Well,
one?
definitely hardware innovation. And indeed, we don't want the qubits to decay either, because then we cannot run deep search. We need to invent new hardware.
So really still a big emphasis on hardware. Kubra, what do you think?
Okay, I will choose the not obvious one, and I will say, how about a ChatGPT moment for quantum computing? And so as a lazy quantum algorithm specialist, if there was a tool that can convert my quantum algorithms and specialize it to any hardware that I want and optimize it for me, that would be super cool.
Oh, I've been thinking that, I've been thinking that same thing. There was recently a news that I think it was ChatGPT. Oh, I think it was an OpenAI in which they did a math contest, and actually their ability to do theoretical math was getting to be incredibly good. Yeah, so I agree. Like, do you think that we could do the ChatGPT for quantum algorithms? And maybe, because I'm not sure what we train it on, but what are your thoughts on that? Is there an AI tool that maybe could dominate in the short term of just helping us make discoveries more efficiently? Would be fascinating.
Yeah, I know there's research going on currently, and we have been starting to work on that as well. So yeah, I think it's not like as involved as ChatGPT, but I know that there are some tools that are trained on for example, the error on quantum hardware or the
Yeah.
gates. So it's not like as improved as what we want today, but I think that would be a great breakthrough to
Yeah.
have that type of tool.
Well, before we move on to I think the taking questions from the audience, I have one last question here, which is that what is that particularly for the audience? What's the one myth or misconception about quantum chemistry and a quantum computer that you'd like to clear up for the audience today? Who would like to take that one first?
I can follow up with what I just said.
Okay. Yeah.
Because people think that, okay, I have a quantum computer and I can use it for whatever I want. So that's not how it works. You have to first be able to map the problem on the quantum hardware. And it depends on which quantum hardware or architecture you are using, what kind of quantum computing model you are using. So, and that's a significant effort as well. That's why I think this myth needs to be eliminated, and people should know that mapping the problem onto hardware is something else.
I see. Yeah, I agree. I think that whole intermediate step is much different than it is for classical computing at the moment. Yeah, for sure. Mario, your thoughts?
Well, I already said my fear that maybe my fear is completely unjust, that quantum chemistry is either identified with Hamiltonian simulation or with ground state finding, and not seeing that these two problems are actually different problems.
Yeah, okay, I think that's a great insight, for sure. Kirstin?
I'm gonna have to agree with my co-hosts that the mapping is the hard part.
Well, I think we're right on time now for questions from the audience. Oh, here we go. I have one. Okay. I do. The first question from the audience, okay, from Shirley. Can quantum computing be used to model high-energy particle collisions like an accelerator like at SLAC or CERN? Dear to two of our hearts because we worked in that field. So I think maybe Kubra, you would like to take that first, or?
Yeah, actually, there's a significant research going on right now in terms of simulating those type of particles. It is either in terms of using hybrid quantum classical models or conducting resource estimation to become ready for the fault-tolerant quantum computing. And also there is quantum machine learning research going on in that area as well for example, detecting anomalies and particles by using the data that has been produced by those experiments.
Oh, so I have a question maybe for Mario, Kirstin, or you, which is as we go to different Hamiltonians, particularly like for quantum chromodynamics, are there really new challenges there, or is it turning the crank? I don't know, Mario, I saw you nodding your head. I mean, if we go to a different, like the lattice gauge calculations, is there something fundamentally different quantum computing can do, or again, it's more adapting the problem to the appropriate quantum algorithm?
Well, there are of course, John Preskill, and so they have these papers on how to simulate quantum field theory, and so I don't see like a huge difference, quite frankly, but maybe I'm completely wrong. Whereas, I mean, like, what is the gauge group that we are simulating, like whether it's U1 or like in the or it's chromodynamics. So I don't see like so once like we know we can simulate quantum field theory, then I don't think that the gauge group matters such a
Yeah. Yeah, interesting. Yeah. That
We
would be
also
very
have
awesome.
some papers on that area, and that's why I think that co-design is important. Like studying quantum field theories using continuous variables is a natural choice because of the fields are continuous. So, but they also have their own challenges, and in terms of the hardware implementation as well.
Yeah, but they discretize it. So they basically they do lattice gauge theory, like they discretize everything.
for the hardware implementation, you mean?
Yeah, for the theoretical work. Of course, we don't have enough qubits to have all those, I mean,
Yeah.
to do the simulation.
Well, I'll ask you all before I take one more question, just on that note. I mean, the other one is the Fermi-Hubbard model that we often have, which is an extremely simple Hamiltonian that seems like, of course, if we can unlock, would do a lot for us to understand spin systems and so on. Again, on a Hamiltonian like that, is there new work to be done algorithmically? Because every few years you see factors of 2 come off the resource requirements. Is there a possibility that there's a clever solution to that? Or again, is it just waiting for the larger number of qubits, of logical qubits, fault-tolerant qubits to come into existence? I don't know if anybody has any thoughts on that. No? Okay, well, we'll move on to the next question from the audience. This one is specifically for Kubra. It's from Arthur. He's in New York City. It says, following your paper, experimentally realizable continuous variable quantum neural networks, have you implemented GKP states on a quantum photonics platform?
So that was a simulation paper because, as I mentioned earlier, continuous variable hardware, like in this case, photonics hardware that we proposed using, has some challenges when it comes to, for example, cloud access, because the algorithms that we design require changing parameters of the photonic quantum circuits, which is hard to do through cloud. Someone needs to go and play with it. And that's why we weren't able to test it on, and this capability is not, as far as I know, is not available on current photonics hardware, but we are looking into collaborating with our experimental colleagues in terms of testing that proposal on quantum hardware. And because in that paper also, we demonstrated that to realize those problems that we studied there, we are in the limits of the experimental capabilities in simulation, but of course, one needs to see what happens on experiment.
I see. No, but are you solely looking at photonic-based computers? Are you looking at trapped ion? I mean, is there anything special about the photonic in your case?
Well, we are not particularly focusing on one single architecture. We have been developing algorithms for various quantum hardware, including quantum annealers, analog quantum hardware, and then qubit-based and photons.
Yeah.
So
I don't see another question in the other, but I'll ask a quick one. We've been talking about all gate-based quantum computing, I think. Does anybody have experience with or thoughts on analog quantum computing? In other words, is there certain Hamiltonians that basically efficiently placed on an analog quantum computer that mitigate some of the near-term problems with noise and so on? Does anybody have any experience with that?
we have a paper online in collaboration with the University of Tennessee, Knoxville, where we studied the optimization problem for power grids or max cut problem in general. But that was more of benchmarking paper and understanding the capabilities of the current quantum hardware.
Yeah. Does anybody else have any thoughts on that, Kirstin or Mario? No? Okay. Actually, that was a question from Ron in Chicago. Thank you, Ron. Okay, another question from the audience. What are your thoughts on the intersection of AI and quantum computing for quantum chemistry? Where can quantum computing help or add on to the functionality of AI-based systems for chemistry? Yeah, I mean, the state of the art's pretty powerful using AI and classical computers. Who would like to take that one on? Anyone? Well, I'll ask it in a different way, maybe. Yeah, Mario.
Yeah, I would just like to say that that's a very domain-specific question, and so I want to say that I cannot say anything because, like, it depends on like I mean, the chemists can only tell, like how can you extract the quantum core of a chemistry problem. How can you separate it from the classical part? Because a chemistry problem, like many chemistry problems, are very classical. Like protein folding, you don't need quantum for that, but then there could be a quantum core. So and then the question is to take your problem apart and identify the quantum part and identify the classical part. And I think that requires a huge expertise in chemistry, and I am certainly not qualified for that, and I'm just that's what I wanted to say. Yeah.
Thanks, Kubra or Kirstin.
I think it'd be
Yeah.
very interesting to see how AI works. I wonder about it some days, given how unique a lot of chemistry or like you mentioned protein, like protein folding is very unique to particular proteins. And I'll grant you, my AI knowledge is very minimal most days. Most days I'm in more of a lab junkie. So spectroscopy, like actual hardware bits. So yeah, understanding how the AI will really apply and how applicable it will be given the uniqueness of a lot of the problems we want to solve. I would really love to see how that would turn out.
Well, correct me if I'm wrong, but I think part of this question could be that, Mario, to your question is that, often you see these hybrid solutions where the classical part sets up the wave function, right? Makes the original guess of the wave function. Then you go, or it sets up, the matrix elements. Then you go through the quantum computer to do obviously the exponential part. And then you come back out and you compare that solution with when you input in the classical loop, you update, say, the wave function, the initial wave, something like that. So I don't know. And then, of course, using AI to try to converge that faster, I think, is possibly the way to do it. But I think that's a general question.
So maybe to these hybrid things, I want to mention that. So there was this American-Japanese collaboration where, like, they connected like the IBM Heron with the Fugaku supercomputer.
Yeah.
And so they studied the two molecules, and there was some intricate like feedback loop where the quantum circuit generates noisy data, and then there is classical post-processing, finds some meaningful configurations, and then it gets fed back. So they have some inventions there. And also there is another group like in Cleveland Clinic, I think, where they are doing some hybrid stuff. So there is out there, but not enough.
Yeah. Okay, great. We do have another question from the audience. To be young, here's the question. What advice do you have for young researchers getting started in this area? Where do they focus their efforts on in terms of the algorithm and or hardware development? I think we've covered this, but where if you were young, where do you think, what should young researchers focus on? Anybody want to take a stab at that?
Find a problem you're interested in. Find something that if you're still in undergrad, find a problem or something that one of your professors has mentioned and you're like, wait, why is that what that is? And go and try it. Find your problem.
Sage advice. Kubra or Mario, any thoughts on that?
I just wanted to say that it depends on your interests, because do you like Mario, do you like working on complexity theories? So go for it, and we definitely need you, and develop really cool algorithms so that we can all experience that moment and look, we can solve this problem with this speed up, and thanks to you, now we achieved all this success. Or are you an experimental person like Kirstin, and do you like getting to the lab and playing with all these cool tools and achieving some cool stuff? Or are you something in between, just like me, and do you like benchmarking the algorithms and at the same time co-designing algorithms for this quantum hardware and developing use cases for various communities so that they can think of those use cases and implement those quantum hardware to their problems. So which of course, this is not limited, but these are three options that you can see here. And how can you experience all of these? There are really cool internship opportunities here in the US. I don't know, I'm sure all around the world as well, but there are these internship opportunities at national labs that you can apply for summer internship, and MITRE also accepts interns. So we would love to work with you. And also universities organize all these summer schools that you can attend. Some of them are online, so you can definitely attend those and see which one you like.
Yeah, 100% agree. And so know yourself and don't solve problems that you don't try, that you don't like. Or so know yourself, what you like. Absolutely, I absolutely agree with that.
Yeah. I would just add there is so much to do in this field, and it's so exciting. Yeah, just do what you love, and in this field, I'm sure you will find a home. And look at, as you said, many labs, many universities have all sorts of internships if you want to get your feet wet on that. So that's all great advice. It's a tremendous field right now expanding, so it's a great time to look at that. Okay, one more question before I give the panel the final one, which is, this is from Cheryl. You discussed co-design of algorithms, applications, hardware. Does this mean the algorithm is different for the type of quantum chip? And if how, can you expand more on this? Ooh, that's a good question. Who would like to take that?
Well, every quantum chip can do any algorithm just with slowdown. So if you have a linear connection between the qubits and your algorithm requires inherently like a grid connection, then you can still do it on a linear, but there is a slowdown. So it's not the question whether you can do it or not, it's the question whether like how much slowdown incurs when you have the wrong design.
I absolutely agree with that. And I saw another question, so I just wanted to connect with that. Quantum annealers for quantum chemistry. And we have a DOE project on that, and we collaborate with Northeastern University to develop designs or algorithms for quantum annealers. So for example, if you want to design it or solve some chemistry problem on quantum annealer, then you have to convert your Hamiltonian into a form that can be implemented on a quantum annealer. But of course, quantum annealers are slightly different than universal quantum hardware, so that's something else. But yeah, in general, you have to consider all the limitations, basis gates, connectivity, error rates, and everything when you are designing your quantum algorithm if you want to implement it on quantum hardware in near term.
I agree. This, I would say, part of the co-design, depending on the topology, are they, like you said, nearest neighbor connections? It can be arbitrary connections, whether or not, you have greater speed in one case, or maybe, your coherence time is much larger. You can tune the depth versus the breadth. So yeah, there's a lot of work to be done here. That's I think we still need to do that. Okay, we have 1 minute left according to my clock. So, and I know that we have to end on time. So the last question, which is to each of you, is, in one sentence, what gives you the most optimism about this field? So I know Kirstin may have to leave first. So Kirstin, you're first.
There's a lot of research. There's a lot of interest. I think with all the interest, there's places to go. So I'm optimistic.
Excellent. Thank you. Kubra.
I think what makes me optimistic about this field is the quantum computing community itself, because they're always open source and collaborating and talking with each other, which is super important in terms of the progress of the field. So that's what makes me optimistic. And all these bright minds being interested in field makes me excited about it.
Absolutely. Mario.
Currently, the cold atom efforts of looking, but if you ask me next year, maybe it will be very different.
Okay, I get what my sentence is. This is, I think, a time possibly like the early days in quantum mechanics itself, which is we don't even know it's possible, but the upside is gigantic. Because you never know the downside, but the upside could be truly transformational. So a great time to be considering the field with a lot of caveats, but still a wonderful time. So we're right on time. I want to thank wonderful Kirstin had to just drop off, but I want to thank panelists for a wonderful discussion. I learned a lot. I'm sure we're all open if anybody has questions in the future to certainly for myself, please reach out and be happy to try to answer anything I can. And I thank the organizers for this wonderful opportunity. And I thank all those who attended and for your questions. Thank you all very much.